Assalamualaikum warahmatullahi wabarakatuh. Selamat petang, salam sejahtera, and greeting to our respected viewers. I would like to welcome all of you to UTM Distinguished Lecture Series and thank you for your support and participation. You are with me, Adnan Hassan, from Industrial Engineering Program, School of Mechanical Engineering, hosting University Technology Malaysia Distinguished Lecture Series number 41. UTM Distinguished Lecture Series is a special program where we invite distinguished and renowned professors around the globe to share their knowledge and experience. And this Distinguished Lecture Series is open to the public through UTM Faculty of Engineering Facebook. We are very sorry that yesterday we could not proceed with the live streaming due to technical issues. But Alhamdulillah, today we will continue our Distinguished Lecture Series number 41, and we hope everything will be running smoothly, inshallah. Indeed, it is a great honor for me to host our honorable guest speaker, Distinguished Professor Duc Truong Pham from University of Birmingham, United Kingdom. It is about 9 a.m. morning in Birmingham, and we really appreciate Prof. Pham's willingness to accommodate to our time schedule. I have known Professor Pham for more than 20 years. It was started when I was accepted as a visiting PhD researcher in his Intelligent System Laboratory and Cardiff Manufacturing Engineering Center, or known as MEC, at Cardiff University, Wales, United Kingdom. During that time, the center was under Professor Pham's leadership. Actually, Professor Pham is not new to some of us in School of Mechanical Engineering, University Technology Malaysia. He was the person who invited UTM to join 4 other universities which had successfully secured 2 European Commission-funded projects known as EPOS, or Advanced Product Support Technologies, which was completed in 2003, and another project, IPSTRA, or Eurasian Network for Product Lifecycle Support and Training, which was completed in 2005. These 2 projects involve Cardiff University in the United Kingdom, Gloucester University of Technology in Germany, University of Patras in Greece, and King Mongkok University of Technology Thonburi in Thailand. Today, we are very fortunate to have Professor Pham with us, even though it is virtually. Professor Pham is going to give a talk on robotic disassembly as an enabler for smart manufacturing. As we know, robotic and smart manufacturing are key technologies as we are moving into Industrial Revolution 4.0. Advances in intelligent systems and robotics will change the future of manufacturing systems. Prof. Pham is a world-renowned authority in this area. To further introduce our honorable guest speaker, I would like to invite Professor Datuk Muhammad Rafiq Abdul Kadir, Dean, Faculty of Engineering. Over to you, Prof. Rafiq.
Thank you, Prof. Adnan, for chairing the session. Assalamualaikum warahmatullahi wabarakatuh, and welcome everyone to our 41st UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq, and I am the Dean of Engineering, University Technology Malaysia. Today, it is my utmost pleasure to welcome Professor Duc Truong Pham from University of Birmingham, United Kingdom. A bit about our distinguished speaker today. Duc Truong Pham received his PhD degree in mechanical engineering from the University of Birmingham, United Kingdom in 1992, and has since made wide-ranging contributions to the theory and practice of mechanical, manufacturing, and systems engineering. His academic output includes more than 500 technical papers and 15 books. He has supervised over 100 PhD theses to completion and has won in excess of £30 million in external research grants and contracts. In addition to pursuing and leading research, He has also been very active with knowledge transfer to industry, applying the results of his work to help multinational companies and SMEs to generate wealth and create and safeguard jobs. He has lectured extensively abroad on his research and has acted as a consultant to several major companies. He was professor invite at École Centrale du Paris, consulting professor at HUST China, Erskine visiting fellow at the University of Canterbury, New Zealand, visiting professor at the University of Paul Verlaine, France, and visiting professor at King Saud University, Saudi Arabia. He is currently a strategic scientist at Wuhan University of Technology. He is the recipient of several prizes, including the Sir Joseph Whiteworth Prize awarded by the Institution of Mechanical Engineers in 1996 and 2000, and the institution's Thomas Stephens Group Prize in 2001 and 2003, and Donald Julius Grown Prize in 2004, and the 5th ICMR Best Paper Prize in 2007. He is a Fellow of the Royal Academy of Engineering, Learned Society of Wales, Society of Manufacturing Engineers, Institution of Engineering and Technology, and Institutions of Mechanical Engineers. He was made an OBE, Officer of the Order of the British Empire, in the year 2003 New Year's Honours List for his services to engineering. So that is a biography of our distinguished speaker today. Here now is Professor Duc Truong Pham from University of Birmingham, United Kingdom, with his talk entitled Robotic Disassembly as an Enabler of Smart Remanufacturing. Professor Duc Truong Pham, over to you.
Hello, thank you very much, Professor Dato Rafiq. It is my honor to give this presentation, and I'd like to thank you and Professor Adnan, my friend, for the opportunity. In the presentation, I will briefly explain what remanufacturing is and why we want to remanufacture. I will talk about smart remanufacturing and then focus on our work on robotic disassembly as an enabler of smart remanufacturing. First, I would like to say a few words about Birmingham, which may not be familiar to some of you. So, Birmingham is the second city in the UK. At 80 minutes away by train from London, Birmingham is truly located at the heart of England. We will host the 2022 Commonwealth Games. My university was established 120 years ago. We have been associated with 100, with 100, I beg your pardon, with 11 Nobel Prizes. Maybe at the end of the year, we'll get to 100 Nobel Prizes. However, perhaps two of our distinguishing features are our world's freestanding clock, which is the tallest in the world, and our own train station on campus. So, what is remanufacturing? It is one of our areas of focus because it is a very important area. According to the British Standard, remanufacturing is the process of returning a product to at least its original condition. Remanufacturing is part of a circular economy, as can be seen in this diagram, which shows remanufacturing forming one of the loops of the circular economy. We are familiar with refurbishing and reconditioning, but remanufacturing is different. Whereas refurbishing is largely aesthetic and reconditioning is about restoring a product to working order, remanufacturing delivers a product that can be considered as new. Why do we want to do remanufacturing? we want to do remanufacturing because it saves a lot of energy, it saves materials, and it also avoids landfill. I had a slide, I don't know why it skipped, and we go to the next slide, which is explaining what remanufacturing consists of. So remanufacturing is a chain of operations. We start with the end-of-life products. We take it apart before we can do anything to it. We have to disassemble it. Then we clean all the components that we have disassembled. We inspect them and we repair those that can be repaired, or we replace those that cannot be repaired. Then we reassemble the product, we test it, and then we have our remanufactured product. So here, this is the slide that was missing. Remanufacture is very advantageous because, as you can see here, for Caterpillar, who is our industrial partner, remanufacturing cuts down greenhouse gases by 60%, cuts down water usage by more than 90%, cuts down energy use by almost 90%, and cuts down raw materials usage by 90%. What is even more impressive is it cuts down landfill by more than 99%. As you can see here, being part of a circular economy, remanufacturing contributes to the 600 billion euros in savings achievable by moving towards a circular economy, as mentioned by the EU Commissioner here. So remanufacturing is smart. It is already smart. Or is it? Is it really smart? In fact, although some large manufacturers, such as Caterpillar, are involved in remanufacturing, the sector has many SMEs. And this quote, which is taken from one of the SMEs, illustrates the problems that they face. Companies are very small size, 20 employees or fewer. Large variety of products, 600 types in this case of turbochargers. And then very low production volumes. So that's the problem facing remanufacturing. Another common problem is uncertainty. This picture shows uncertainty in the condition of the product at the end of its service life. There are other uncertainties, as we shall see later. To overcome uncertainties, we need smart remanufacturing. Now, you are probably more familiar with smart manufacturing and digital manufacturing, but we also have the equivalent in remanufacturing. So we have digital remanufacturing and smart remanufacturing. Another name for smart remanufacturing is remanufacturing 4.0. As you can see from that name, it is about using Industry 4.0 technologies to make remanufacturing smart. This familiar slide shows Industry 4.0, the fourth industrial revolution, and the previous industrial revolutions, starting from the first one, which actually has its roots at Birmingham, right here in Birmingham. So, what are the technologies involved in smart remanufacturing? In fact, they are technologies of Industry 4.0. You will see they include sensors, autonomous robots, cyber physical systems, and the Internet of Things. So, here are some of the uncertainty problems in smart remanufacturing. They are uncertainties with the supply of the end-of-life products and in the demand for them. There are also operational uncertainties caused by the variable conditions of end-of-life products. Sensing, monitoring, prediction, together with communication and big data and machine learning, can help overcome problems due to those uncertainties. So these are the techniques, and you recognize them as Industry 4.0 techniques. There are further issues with remanufacturing, not only uncertainties, but there are these small production batches. So batches sometimes of one made to order, that is not uncommon. Also complications with materials management and resource planning, complex shop floor scheduling and control, and so on. And again, we see that technologies of smart automation, of smart sensing, of accurate modeling and prediction, these technologies can help overcome problems in remanufacturing and make remanufacturing smarter. This slide summarizes the links between Industry 4.0 and remanufacturing to give smart remanufacturing. The left-hand side lists the key the left-hand side, lists all the key Industrial 4.0 technologies. And the right-hand side, the areas of remanufacturing that can be made smarter. So by applying the technologies on the left-hand side to the problems on the right-hand side, we create smart remanufacturing. Here is a little quiz for you. What does this slide, which comes from Caterpillar? So it shows the disassembly of an engine at Caterpillar. What does this slide imply? What does it show? Yes, you are right. It shows that disassembly is very labor intensive. It is costly and represents a major obstacle to widespread adoption of remanufacturing because of the cost of disassembly, the difficulties involved, the problems that require human intervention. So, we have been focusing our efforts on this problem of robotic or of disassembly in order to create robotic disassembly, in order to address this bottleneck in remanufacturing. We want to understand disassembly processes fundamentally. Our aim is to create robust autonomous disassembly systems that are reliable, that can work without fail. And our approach to this problem is to adopt a multidisciplinary approach, which involves manufacturing engineering, mechanical engineering, electronics engineering, computer science, data science, in order to understand the problem and devise solutions to them. So, we study over the past 5 years disassembly science. We study disassembly processes, the fundamental disassembly processes, to determine the patterns recurring in disassembly problems and the physical and cognitive efforts required to solve them. With our understanding of disassembly, we devise practical strategies for carrying out disassembly. We also work with partners at the other universities abroad on disassembly planning. And our aim is to develop optimal plans for disassembly in order to save time and save cost. We also realize that disassembly is a complex process. Not all of it can be done by machines. So there is a need to involve people in some cases. There is a need for people to work together with machines. So we have been looking at collaborative disassembly. And in our work, we have developed practical demonstrations. I'm going to go through all these 5 points. This next slide shows the 5 points again, but in diagrams, in pictures. So here we look at disassembly signs. We look at how we remove a pin from a hole, for instance, or how we undo a screw. We look at disassembly strategies. After we understand the mechanics of the process, we can then devise clever strategies for machines to perform them. We look at disassembly planning with our friends at other universities, at our partners in Wuhan and in Spain and in Beijing. We look at collaborative disassembly involving people and machines, and then we implement a number of demonstrations. So for the rest of this talk, I will describe these various activities. Before we carried out our research, we examined a lot of products to find the common operations, the common disassembly operations. So we studied over 400 products, and we found something like 12,000 operations. We classified them into broad classes. We found that about 40% of them involve unscrewing. Another 20% involve taking a pin out of a hole, you're pulling something from a hole. So about 60% are these fundamental processes, and then another 40% are different miscellaneous separation processes. So we focus our efforts on the 60% of the operations. We study robotic disassembly of like unscrewing operations. We use finite elements modeling to study unscrewing operations, the fundamental ones. We also looked at the unscrewing of real products like this turbocharger. Again, finite element analysis. We do experiments. We look at the removal of a pin from a hole. This is an interesting operation. When I did my PhD, I studied how to put a pin into a hole. Now, many years later, I look at how to take a pin out of a hole. So our colleagues have been studying this process fundamentally. They have looked at the mechanics of it, and they've also looked at this finite elements analysis of the process. At the end of life, many products are affected by corrosion. So we study how corrosion affects screws and the efforts required in removing screws to see how we can overcome this corrosion, how much torque we need to apply extra in order to remove screws and nuts that have been corroded. So this shows our study of the removal of a pin from a hole. Now, when I did my PhD, we looked at compliance as a strategy for helping assembly. So now we look at how compliance can help disassembly. And we have written an interesting article on this, which I can share with you if you are interested. We have implemented this in real experiments. So we use a combination of passive accommodation and active compliance. So this robot uses active compliance, and at the end of the robot, there is also a passive compliance device to help it to perform the disassembly process. Here, we study a different disassembly problem. The removal of a latch from a slot. And you can see on the left-hand side, the robot uses compliance alone. So although it succeeds in the end, it performs the operation much more slowly than on the right hand side. On the for the case B, the robot started later and it finished earlier. So the difference there is that the robot in case B uses compliance as well as vibration. So we study the use of vibration to reduce the forces in disassembly and also the time required. Yeah. So the demonstration showed that. As I mentioned before, one of our activities, a very major part of our work, is to study disassembly planning. So here is a very simple disassembly, the disassembly of a water pump. And we study different plans for disassembly this pump. So you can see this is the first plan, this is the second plan, and the third plan is shorter. So it saves time. Now for this simple process, the time savings are not major. But if you have a complicated disassembly, an optimal plan can save a lot of time. So we are looking at the use of optimization to devise optimal disassembly plans. We have built a demonstration disassembly cell. And in this case, the cell is used to disassemble this water pump that you saw earlier. There is a video of this cell performing the disassembly of a water pump. And you can see that the cell consists of two robots. They are collaborative robots, a human operator, and peripheral equipment. I will let you have a look at the video in your own time. If you visit our website, you will see you will be able to see the video. You can also find the video on YouTube. For this presentation, I will focus on a different demonstration. So here is the disassembly cell again, but reconfigured for the disassembly of a turbocharger, slightly more complex operation. And in this case, I show the human-robot collaboration at work. So you will see that during the operation, there will be some tasks that the robots cannot perform, and the human comes in to perform those tasks. So here you have the operator performing some tasks. Some tasks are done in common with the robots, and some tasks are done by one robot, and some tasks are done by the other robot. So I have a short video of about 3 minutes to show you now. So the operator comes in. So the turbocharger is picked up by one robot, puts into a clamp. The second robot performs the disassembly, the unscrewing operation. So unscrewing is being performed. The robot has to search for the location of the screw. Now unscrewing is happening. The robot uses force sensing to search for the screw. Yeah, you can see the searching operation again. Yeah, so the unscrewing happens now. I'm sure. Yeah, you can see. So the human operator comes in and performs some operations that the robots find difficult to do. So in this presentation, I have briefly explained remanufacturing. I then talked about smart remanufacturing and then focused on robot disassembly. Remanufacturing is economically, socially, environmentally beneficial. Before any other operation can be performed on an end-of-life product, it must be disassembled. Currently, disassembly is very labor-intensive because of the uncertainties discussed before. This raises the total cost of remanufacturing and prevents its widespread adoption. Our Auto Reman project investigates the use of Industry 4.0 technologies to produce smart remanufacturing that can handle uncertainties and offer the required efficiency and flexibility. I'd like to acknowledge our University of Birmingham team, our UK partners, industrial partners, and technology translator partners, our international partners, Wuhan University of Technology in China, University of Castilla-La Mancha in Spain, Beihang University in China. I'd like to end the presentation with this quote from the EU Commissioner for the Environment. You can see then that remanufacturing is a very important activity. It is very beneficial and it has many potential benefits. It deserves to be applied in a very widespread fashion. We would like to invite you to join us to achieve the aim of widespreading remanufacturing. Thank you. Terima kasih.
Okay. Okay, terima kasih, Prof. Now you learn bahasa. Okay, thank you.
Thank you very much.
Thank you very much. Thank you very much, Prof. Pham, for your informative, insightful, and interesting sharing. And on behalf of UTM and all our viewers, okay, we would like to express our deepest appreciation for your inspiring and interesting presentation. I'm sure there are some questions. We will take some questions. Is it okay, Prof?
Yes, certainly. Certainly.
Okay, maybe I can start a simple question first. Okay, in the era of automation, intelligent system, how about the issue of security in smart manufacturing? What are the requirements that we need to be prepared, to make it smart manufacturing secure?
Okay, So that's a very good question, Professor Adnan. Our focus has been more on safety rather than security. We've
Okay.
been focusing on how to make people safe and robots safe and equipment safe. So that is our top priority. We have not been focusing on security. We do have colleagues in our computer science school. They work on security, but our focus is really on safety.
I see. Okay. Okay. So actually, it's a big research area, right?
Yes, yes, yes.
Okay.
You
Okay.
know,
How do you? Okay.
carry
Proceed,
on,
Prof.
please. Yeah,
Yeah.
carry on.
Okay. We see that now robots are replacing human being in terms of manual and repetitive tasks. How do you see the role of human operators in the future? Do we have
Okay,
any?
yes. So for manual repetitive tasks that are that do not require, dexterity, high degree of dexterity, that do not require access in difficult areas, then those tasks can be robotized easily. In the future, humans will still be required for tasks that require cognition, a lot of decision making, um, high dexterity, access to difficult areas. So humans will still be required, but there will be more and more tasks that can be done by robots. And in the meantime, human robot collaboration will still be useful. And our work shows that there are areas that are too not technically difficult, but too expensive to robotize.
I
In
see.
order to enable robots to perform some tasks, you have to design tools that are specialized, and they take a lot of time to design and a lot of cost to buy. That's why I think in many cases, humans are still required in at
I
least in disassembly. Yeah.
Okay, you mentioned that your project is this Autoreman, right? Autoreman. This is
Yes.
related to Industrial Revolution 4.0. So in the UK perspective, how far you think that this Industrial Revolution 4.0 is being practiced? Is it becoming a common, strategies in manufacturing now in the
It
UK?
is commonly talked about, but quite a few industries, quite a few companies are still working in industry 2.0, industry
I see.
3.0. But industry 4.0 is the aim rather than the actuality.
I see. So we are still far away, is it?
For many
For,
companies. For some
for many.
companies, they already apply Industry 4.0. The big companies like Siemens and so on, yes, they are very advanced. But there are other companies, the small manufacturers that I mentioned earlier, the remanufacturers,
Mhm.
the 20 people companies, they still are using Industry 2.0 and Industry 3.0.
I see. So I remember that okay, when I visited your intelligent system laboratory last time, I learned about pattern recognition. Can you comment what is the role of pattern recognition in smart manufacturing?
Yes, yes. So one of the applications is in our work is in recognizing the forces that a robot experiences when it performs an operation, like taking a pin out of a hole or disassembly a screw. You saw in the demonstration the robot searching for the screw, searching for the nut in order to be able to undo it. So that requires pattern recognition. That requires measuring the forces that the robot experiences and then determining where the robot is. So yes, sensing pattern recognition is necessary for advanced systems, for smart manufacturing systems.
I see. Okay. Do we have any question from the audience? So I think your lecture has been very clear enough, Prof. Everybody understood well. There is no question from the floor. Perhaps should I pass it to Prof. Rafiq if you have anything to say, Prof. Rafiq?
Well, first of all, I must say thank you so very much to our distinguished speaker today for accepting our invitation. You know, Prof. Duc Pham, you mentioned about that there was one video on Caterpillar engine tear down. That was
Yes.
really amazing, you know, in terms of a very labor intensive, you know, the way that, you know, how many how many people are required in order to tear down an engine. That is certainly an interesting video. And you also mentioned about the finite element analysis. You know, when you completed your PhD, it's all about taking pin in, and
Yes.
this thing is about taking pin out. I guess
Yes.
it's the same story. In my case, a PhD for my PhD, I completed a finite element analysis on hip arthroplasty. Yeah. Hip arthroplasty. So that's a simple analysis. Back then, it was something like 2005. Yeah, but something like 15 years ago. But nowadays, they have done a more complex analysis using finite elements. So it is certainly interesting to see that one as well. And then another interesting point, Prof. Duc Pham, you mentioned about Industrial Revolution 4.0, that most companies are still in IR 2.0 and 3.0. Yeah, that's a fact. I mean, even here in Malaysia, most of the companies here are still on IR 2.0 or 3.0. I've seen one company, if I'm not mistaken, it is Western Digital. That company, they showed a video of their manufacturing floor, 100% robotics. 100% robotics, no human whatsoever, and that factory operating 24 hours a day. Certainly amazing to see that one.
Sure.
And anyway, Prof, certainly amazing to see some of the very nice pictures on your slides. Again, thank you so much for accepting our invitation, and to all of the viewers, all our global audience watching this distinguished lecture series. Thank you so very much for watching. Do stay tuned because we have many more lectures for you. Until then, bye bye for now. Bye bye.
Bye-bye. Thank you very much. Thank you.
Thank you very much, Prof.
Bye.
Thank you.
Bye.